What's the smallest thing that you can think of? Yeah, right there.
Air.
Air. Okay. Good guess. Good guess. You right there in the front.
Oh, atoms.
Okay. Even better. I love that one. Can anyone think of anything smaller than atoms? Right there.
Quarks.
There you go. Now we're getting small. I love these answers. Good job, guys. So today, we are going to explore a realm that is so tiny that regular rules that govern the world around us that we can see start to work very differently. So my name is Ari Nouri, and I'm an engineer and scientist here at IBM Research, and I work on something called quantum computing. So who here has heard of quantum physics? Just raise your hand. Who's heard of quantum physics? Wow, a lot of you guys. That's great. So a lot of people say that quantum physics is really hard and, it's hard to understand. Nobody can understand it. Well, what if I told you that all of you here are going to leave here today with a better understanding of quantum physics than most people in the world? Cool, right? So today we're going to go on an adventure to discover two amazing things. First, we're going to learn about the world of quantum physics, and then we're going to learn how scientists here at IBM are using quantum physics to solve some very important problems. But before we dive into the quantum physics, let's first travel back in time, all the way back from 2025 to the year 1687, to learn about something called classical physics. So does anyone know who this guy is? Raise your hand. Yes. Isaac Newton, that's right. So if you don't remember Isaac Newton, he's the guy that was sitting under the apple tree doing some studying, and the apple fell on his head, and then he discovered gravity. So Isaac Newton, he did work all the way back in the 1600s to help invent the field of what we call classical physics. And classical physics essentially describes how normal-sized objects that we can see, like you or me, or this tennis ball, move, right? So Isaac Newton and many other scientists back in the day figured out how regular-sized objects move very, very precisely. And classical physics is so precise that we can even use it to send huge rockets into space and bring them all the way back down to Earth. Cool, right? So if I drop this ball, of course the ball falls. That's gravity. That's part of classical physics. And if I bounce the ball on the ground, it comes back up. That's also explained by classical physics. And so let's call this tennis ball my classical tennis ball. So this yellow one, that's my classical tennis ball. And this classical tennis ball follows the rules of classical physics. But then 200 years later, this guy came along. I want us to all say his name all at once. 1, 2, 3.
Albert Einstein.
Albert Einstein, right? The most famous scientist in the world, probably. So about 200 years later, Albert Einstein and his friends, they came along and they made a very mind-blowing discovery. They found out that really, really tiny things like atoms, like you said, and quarks, they found out that things don't follow the same rules that Newton discovered many, many years ago. Those things follow a new set of rules for how really tiny things interact with the world. Those set of rules are called quantum physics. So how tiny? And you guys were really smart. You guessed. At the scale of atoms, at the scale of individual molecules, right? So how big is an atom, right? It's way, way, way smaller than a grain of sand. A grain of sand actually has billions and billions of atoms in it. So we're talking about things so small that you can't even see them with a microscope. So when we start studying things that are really small, we find out that they can do crazy things that are really impossible for big things to do. So let me show you what I mean. So remember we had my classical tennis ball here. And if I throw this classical tennis ball against the wall, it bounces right back at me, right? But now let's use our imaginations and pretend like I have a quantum tennis ball. So this one's kind of orange. This is my quantum tennis ball. And let's pretend that this quantum tennis ball follows the rules of quantum physics. So sometimes in the quantum world, if I were to throw this quantum tennis ball at this wall, there's a chance that when this ball hits this wall, it'll actually go right through. It won't bounce off. It'll go right through the wall. And that's just one of the many really weird things that can happen in quantum physics. So one very important takeaway that I want you guys to understand is that very tiny things in the quantum world follow different rules than big things in the classical world. So let me give you some more examples. So here, I have a penny. And just like, yeah, big penny, right? And just like my quantum tennis ball, let's use our imaginations to pretend that this penny is actually a quantum penny. So this penny, our quantum penny, has two sides. It has a heads and a tails. What side is that? Tails. What side is this one?
Yes.
Perfect. Excellent. So how do you determine what side the penny is? What do you have to do? Easy question. You got to look at it. Right, exactly. So now I'm going to spin this penny on the table. So while this penny is spinning, do we know what state it's in?
Heads.
Okay, I'm going to ask you a question. Who thinks it's heads while it's spinning? Who thinks it's tails while it's spinning? Who thinks it's neither? Okay, good. So in the quantum world, when the penny is spinning, it's in what's called a quantum superposition. And what that means is that the penny can exist in some state that is both heads and tails. Now, if we want to observe what state the penny is in, what do we have to do when it's spinning? We have to stop the penny, we have to look at the penny, and then we can observe whether or not it's heads or it's tails. So just like our quantum penny, there are objects, really small objects, that live in the quantum world, like atoms and like molecules. They can exist in a combination of states that is made up of many different distinct states. And the key point here is we can only know the state of our quantum object, like our quantum penny, if we stop and observe that quantum penny. So now next, I have a second quantum penny. Now in quantum physics, when you have two quantum things that interact with each other, in this case, two quantum pennies, they can become connected to one another through a special quantum link. And that special quantum link is called entanglement. Now, when these two quantum pennies become entangled with each other, they make a promise to one another that no matter what, if one penny is heads, the other one will promise that it will also be heads. So, if I spin both pennies, what happens? I bring them into a quantum superposition. Now, if I want to know the state of both pennies, all I have to do is stop one, look at one, and I see that this one's heads. And the second that I looked at this one and saw that it was heads, I immediately knew that this one was also heads without even needing to look at it. And this works even when the pennies are super, super far apart. So if I take this penny and I keep it here in New York, and then I give this one, and I threw it all the way to California or something like that, if I were to flip or spin my penny here in New York, and I were to look at it and see that it was heads, I would immediately know that the one all the way in California is also heads. Even though I don't have it, even though I'm not looking at it, I would know the one in California is heads as well. So Einstein, he thought this was crazy. He actually called this spooky action at a distance. Okay, so these are the three strange quantum properties that we learned about today. The first one was quantum tunneling, where our quantum tennis ball, if I threw it against the wall, it would go right through. The second one was superposition, that quantum objects can exist in states that are a combination of multiple distinct states. And the only way to know the actual state of a quantum object is to stop and to look at it. And then finally, quantum objects, they can become entangled with one another through a special quantum link, such that they make promises to one another that if we know the state of one, we immediately know the state of the other. Okay, so we're going to go back to this key takeaway number one. Tiny things that live in the quantum world follow different rules than big things that live in the classical world. Okay, so that's cool, right? But now that we know that quantum objects can do strange things, what can we actually do with that in the real world? So let's imagine a story together about a scientist named Dr. Lauren. So what does Dr. Lauren do? She tries to solve hard problems to make the world better. That's kind of what a scientist likes to do. So, in order to solve tough problems and make the world a better place, scientists use a lot of different tools to help them. So what's an example that you guys can think of a tool that a scientist uses? Yeah. Chemicals, that's one. Yep. Microscope, that one's very commonly used. Anyone else? What are some other tools? Magnifying glass, good one. Right there.
Tubes.
Test tubes. What do you guys think is the most used tool by scientists? The most. Right there in the blue. A computer, yes. Excellent. Computers are probably the most used tool by scientists. They use them all the time. Look, I have one right here. Every single day when I come into work and do science, I use my computer. And so does everyone else here at IBM. So Dr. Lauren, what she's trying to do is she's trying to discover a medicine that could cure a very, very serious disease. And so to do this, she needs to understand exactly how tiny molecules will interact with one another at the quantum level. And so first she tries using her laptop to calculate how these molecules behave. But when she runs her program, her computer says, this will take 100 billion years to complete. So Dr. Lauren gasps. She says, that's longer than the universe has even existed, right? I need a faster computer, she thinks. So she goes out and she buys the newest, fastest, best computer that she can. And do we think this is going to solve her problem?
No.
No, unfortunately, no. Even with the fastest computer, 99 billion years the calculation will take. So she's getting desperate. She calls her friend at IBM. She says, I need the fastest and best computer in the world. And her friend says, I have exactly what you need, and invites Dr. Lauren to come to IBM. And so when she arrives at IBM, her friend takes her to this enormous room filled with this gigantic supercomputer with rows and rows of powerful machines all working together. Now, it's the fastest computer in the entire world. So Dr. Lauren excitedly loads up her program and runs the calculation again. But even this amazing supercomputer displays 90 billion years to complete. So Dr. Lauren slumps in her chair, she's all defeated. Even the world's best classical computer can't solve her problem fast enough. So while she's sitting there looking sad and distraught, another scientist named Dr. John notices her and asks her what's wrong. So she explains, I'm trying to understand how these tiny particles interact with one another. So Dr. Lauren says, but even the best computer in the world would take billions of years to complete. But then Dr. John's eyes light up. He says, aha, you have discovered something very important. Some problems are practically impossible for even the best normal computers to do. Because your molecules are quantum objects, they follow the rules of quantum physics. And classical computers just are not built to handle quantum information efficiently. So Dr. Lauren has a breakthrough idea. She says, what if we built a different kind of computer, one that uses quantum physics itself to solve quantum problems? And that's exactly what they did. Instead of using classical bits like normal computers, they designed a computer that works with the rules of quantum physics. So quantum computers are ultimately a tool to solve very special problems in the quantum world that are impossible to do on a normal computer. And these are pictures of what you'll see on the outside of a quantum computer. And these are pictures of the inside with all our special scientific equipment. And so ultimately, how does a quantum computer work? And the second thing that I want you guys to remember today is that quantum computers use the special properties of quantum physics to solve problems that are impossible for a classical computer. So remember our three quantum properties: quantum tunneling, superposition, and entanglement. These are some of the things that a quantum computer uses in order to solve special problems that are not possible to do on a normal computer. So a quantum computer uses something called qubits, or what are known as quantum bits. And these qubits, they follow the rules of quantum physics. Now, qubits can exist in a state of superposition, and they can become entangled with one another, just like our quantum pennies, exactly like our quantum pennies. Now, to make our quantum computers actually work, we have to cool the inside down to colder than outer space, actually about 100 times colder than outer space. And so when we close up this quantum computer in these white cans and we cool it down, our quantum computers actually get as cold as minus 460 degrees Fahrenheit. That is one of the coldest places in the known universe. Okay, so let's do a quick recap about the story that we just told, right? Scientists in general, what they try to do is they try to solve super hard problems and discover new things to make the world a better place. But some problems that involve very, very tiny objects like atoms and molecules are impossible to solve for even the fastest normal computers. Now, very tiny objects that live in the quantum world, they follow special rules called quantum physics. And a quantum computer uses those special properties of quantum physics to do things that are impossible for normal computers. So remember, key takeaway number one that I want everyone to remember today. Tiny things in the quantum world follow different rules than big things in the classical world. And number two, quantum computers use special properties of quantum physics to solve problems that are impossible on a normal computer. So what are these types of problems that we're talking about? So remember the story of Dr. Lauren. She was trying to find a new medicine to cure a disease by understanding how tiny molecules will interact with one another. We can also do some very great things with quantum computers by creating new amazing materials, for example, for something like a plane, something very strong, but also very light, by figuring out how atoms will stick to each other, for example. We can also help solve big climate problems by discovering potential better ways to, extract carbon from the air or make cleaner fuels. But ultimately, there are many more things that we have yet to discover that we can use a quantum computer for. So when quantum computers will help us solve these special problems, scientists can create amazing new technology that will ultimately make the world better for everyone. So one day you might be the scientist who's using a quantum computer to invent something incredible that helps people all around the world. But one thing to keep in mind is quantum computing is not ready yet. We need more scientists like you to help us get started and to help us really make an impact. And so if you're interested in working in quantum computing and studying in quantum computing, here's what I would recommend. I would do what I like to call discover your superpowers. Figure out what you love doing and what you're good at. Do you like math? Do you like art? Do you like solving puzzles? Do you like building things? Do you like writing stories, right? And then find a way to apply what you love to quantum. If you like solving puzzles, then one day you could help find new ways of solving problems using a quantum computer. But the most important thing that you guys need to remember is keep learning science. Science isn't just about experiments and fancy tools like a quantum computer. Science really is a powerful way of thinking that will help you succeed and do anything in this world. You don't have to be a scientist as a job to think like a scientist. Science gives you the foundation to do anything you want in this world. And thinking like a scientist will help you in everything from playing sports to doing art or to even playing music. So the world needs more scientific thinkers like you to solve problems and make the world better. And that's what a scientist does every day, and you can too. So thank you so much, everyone, for listening, and thank you for your interest in science.